All right, welcome back, you guys. We're going to take a look. Welcome back to your favorite Calculus 2 class, of course. We're going to look at these alternating series tests. So far we've dealt with mostly series that have had positive terms. So now we're going to look at ones that have alternating series. So here's an example of an alternating series right here, or you can write it this way with that -1 to the n. Of course, this is indicating that your signs are going to change each time, right? -1 to the n power times 1 over 2 to the n. So this is an alternating geometric series. Again, you're looking for alternating terms, right? It's going from a positive to a negative to a positive to a negative and so on. Or vice versa. Maybe it starts out negative and then it changes to positive and negative, positive, and so on. So for an alternating series test, it will converge when two conditions are met. The limit as n goes to infinity of a to the n equals 0, and the next term is less than or equal to the prior term for all n. Okay, so decreasing or the same. So let's go ahead and use this alternating series test for this first one here. So, if you were writing it out, of course, you would say, well, if n is 1, I'd have -1 to the 1 plus 1 times 1 over 1. So I'd have -1 squared times 1, which is just 1, plus, then I'd plug 2 in, -1 to the 2 plus 1 times 1 over 2. And notice that's a -1 to a third power, so that'd be a negative, right? So it'd go from a positive to a negative to a positive to a negative and so on. Dot, 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 right? This part right here is making it alternate. Okay, that part right there is making it alternate. So if I look up here at the alternating series test, is if I ignore the alternating part, that's my a subscript n, and that's what I want to analyze here for number one, for the conditions being met. Does the limit as n goes to infinity of ignoring the alternating signs, does the limit as n goes to infinity of the a sub n, the part that's not alternating, does this equal 0? Number one. That's the first condition it's got to meet. So that's got to be true first for this to converge. So we have limit as n goes to infinity of 1 over n. Does this equal 0? And we say, sure enough, it does. That's true. 1 over infinity equals 0. So I go on to number 2. Is the second condition met? Is a sub n plus 1 less than or equal to a sub n for all n? Well, remember, a sub n is 1 over n. So a sub n plus 1 would be 1 over n plus 1. Is that less than or equal to 1 over n? Yeah, exactly. Like if you let n be 1, it's true. For any n, right, this will be true. So that's true also. Yes, it is. And so you say, therefore, since the two conditions are met by the alternating series test, the series converges. Now let's take a look at this one. Determine the convergence or divergence of. And let's make sure that this thing alternates. Let's let n be 1. If n is 1, I got 1 over -2 to the 1 minus 1. Or 1 over -2 to the 0. So anything to the 0 is 1. And hopefully you can see it does alternate signs, doesn't it? So it goes from a positive to a negative to a positive and so on. So let's apply the alternating series test. Well, the hard part on this one is, what's the we need to find the part that's not alternating on this. What's the a sub n part? This is what we have, negative 2 to the n minus 1. Well, that's the same as negative 1 times 2 to the n minus 1. Well, that's the same as negative 1 to the n minus 1 times 2 to the n minus 1. So here, this is the alternating part right there. So in green, that would be the part that's not alternating the signs in green. So an is n over 2 to the n minus 1. That's what we're going to use for the part that's not alternating signs, right? So now we can apply the alternating series test. So the question is this 0 question mark? Well, let's find out. A sub n is n over 2 to the n minus 1. So notice we have infinity over infinity by L'Hopital. So I'm going to apply L'Hopital's rule on this. So that'd be limit as n goes to infinity. Derivative of n is just a 1. And then take the derivative of the bottom. I got natural log of 2 to the n minus 1. Derivative of n minus 1 is just a 1. Now I run this to infinity. I throw the infinity in. So I got 2 to the infinity on the bottom. So I got 1 over infinity, which is, sure enough, that's 0. That works. So the first condition is met. So then the second question is this true for all n that we have? Remember, we have a to the n is n over 2 to the n minus 1. So I got n plus 1 over 2 to the n plus 1 minus 1. So I got n plus 1 over 2 to the n. Is this true? And maybe it's hard to see, like let's let if n is 1, then I'd have 1 plus 1 over 2 to the 1. Is that less than or equal to 1 over 2 to the 1 minus 1, which is 2 to the 0 or 1? That's for n being 1. And so in other words, is 2 over 2 less than or equal to 1 over 1? That's true, right? What about if n was 2? Then I'd have 2 plus 1 over 2 squared is 3/4 less than or equal to 2 over 2 to the 1. It's 3/4 less than or equal to 1. Yeah, that's true. You could keep going with this. And you have 3 plus 1, I got 4 over 2 to the third is 8, less than or equal to 3 over 2 squared 4 is 1/2 less than or equal to 3/4. Yes, and so on, right? You can see you can keep going with this. So by inductive reasoning, yeah, that's going to be true as well. Therefore, by the alternating series test, since it passes those two conditions, the series does converge. The original alternating series converges. All right, let's go ahead and notice that the signs here do alternate. I got 2 over 1, then I got a negative 3/2, and a positive 4/3, and so on, right? And so right here is my a sub n part that's not alternating signs. So number 1, let's apply this alternating series test as the limit as n goes to infinity of the a of n equals 0, question mark. Well, that would be the limit as n goes to infinity of n plus 1 over n. That's infinity over infinity. So let's solve this algebraically instead of with L'Hopital's this time. Let's divide everybody by n. So we got limit n goes to infinity of 1 plus 1 over n all over 1. This goes to 0, so I got 1 plus 0 over 1. So this is 1. This is not 0. So we say, so alternating series test, right? This condition is not met. So we can quit right now. Alternating series test does not apply. And even though, actually in this case, a to the n plus 1 is less than or equal to a to the n, the other condition is met, but it doesn't matter because this one wasn't. All right, so I'm not even going to bother to test it, the other condition. So alternating test is no help. Note, however, though, using the nth term test of divergence, this is 1, which is not 0. Therefore, it diverges. And the alternating series would also diverge, right? If the series that's not alternating diverges, then the one, even with alternating signs, is also going to diverge too. We don't have a formula for this. Note that the signs, they do alternate on this. Yeah, you get positive 2 over 1, negative, positive, negative, and so on. So we are going to try to use this alternating series test. Let's see if we can get a formula for this. See how if n is 1, this might be the easiest way to see this formula here. If n is 1, you see how you got 2 over n minus 1 over n? And then if n is 2, I got 2 over 2 minus 1 over 2. If n is 3, you got 2 over 3 minus 1 over 3. You see that? So this is 2 over n minus 1 over n. The signs do alternate. You can write that, that's a common denominator. So I got 2 minus 1 all over n. So it's just 1 over n. All right? So let's apply alternating series test on this. So number 1, so the limit as n goes to infinity of a sub n equals 0. Yes, that's true. How about number 2? Is this true for all n? Well, if I have, let's look at our terms for a minute. I got 2, and then I have negative 1 over 1, and I got 1, then I have a half, right? My terms that were listed, and I had, and you know what? Let me I need to ignore my signs for a minute. This is just for the non-alternating. So I had 2, 1, 1, negative a half. Again, I'm ignoring the signs, so a half. Then I got 2/3. I got 1/3. That's terrible. 1/3. I got 2/4. I got 1/4. So is the next one less than or equal to the prior one? So is 1 less than or equal to 2? Yes. Right. This is the first term, second term, third term, fourth term, so on. So yeah, that's true for those two. Let's do the next one. Is that one less than or equal to the 1? Yeah, that's true. Is 1/2 less than or equal to 1? Yeah. Is 2/3 less than or equal to 1/2? No. See how that's going to fail right there? So as soon as you get one that doesn't work, right? Remember, it's got to work for every time. Every time. So this is not true. So fails here. So alternating series test does not apply. Well, we had it in a form. Note that we had it in this form cleaned up 1 over n. So we could just use the p-series anyways, right? So we can actually analyze this using the p-series test. 1 over n to the p, where p is 1, so I'm less than or equal to 1, greater than 0. Therefore, it diverges by the p-series here. Well, occasionally you guys, you'll have a series that has positive and negative terms, but it's not alternating every time. You know, it's not going positive, negative every time, but it still has some positives and some negatives. All right, so that's an example right there. So one way to obtain some information about the convergence is to investigate the convergence of the absolute value of it. And then applying, in this case, you could apply your direct comparison and see that it converges by the p-series. So the absolute value converges as well. And so you have what this is called the absolute convergence here. So if your absolute value converges, then the series will also converge. Okay? But the converse is not true. Just because the original series converges does not mean the absolute value will converge. Okay? So that brings us to right down here. So that's the difference between absolutely convergent and conditionally. So number one, if your series, the series is absolutely convergent when both the original is convergent and the absolute value converges. When they both converge, the series is absolutely convergent. When the original converges but the absolute value diverges, that's conditionally convergent. Okay. That's conditionally convergent. So let's look at that for this one here. So here's example 5. Determine whether each of these series converges or divergent. So number one, notice, see how the signs alternate? This is an alternating series. All right, we're starting with 0 this time though. All right, it does alternate. So number one, there's a limit as n goes to infinity of a sub n equals 0 question mark. Well, the a sub n, the non-alternating part here, is the n factorial over 2 to the n. Bless you. N factorial over 2 to the n. It might best be look at this with a table of values, but as n gets substantially big, right, increases in magnitude, as n goes to infinity here, your 2 to the n, your n factorial, this is substantially larger than the 2 to the n part as n goes to infinity, right? That n factorial is way bigger than that 2 to the n. And so this goes to infinity, which is not 0. So this is not true. Right? This is not true. By the way, a to the n plus 1 is not less than or equal to a to the n either. The second one also fails too. But as soon as you see one fail, I say, well, we can't use the alternating series test. We can use the nth term test though. So the limit n goes to infinity of a to the n. That is not zero. Therefore, the series diverges. Okay. Well, if you notice the alternating signs on this, n is 1, n is 2, see how this goes positive, negative, and so on. So let's go ahead and apply the alternating series test. And that's the alternating part, the negative 1 to the n. So I want to take the non-alternating part and see if that's equal to 0. So just the 1 over square root of n. You send that to infinity, and sure enough, that does equal 0, so that's true. Does a to the n plus 1 less than or equal to a to the n for all n? Question mark. Well, 1 over square root of n plus 1 is less than or equal to 1 over the square root of n. That's true. So by the alternating series test, then, it has the two conditions. That means this alternating series does converge. Converges. So the question is then, is it conditionally convergent or is it absolutely convergent? So let's examine the absolute value. So we have negative 1 to the n over square root of n, which is just 1 over square root of n. And by p series, 1 over n to the p, our p here is a half. 1 over n to the 1/2, right? 1 over. So our p here is less than or equal to 1. Oops, greater than 0 here. This would then diverge by the p series. So what can we conclude? Well, the original series converges, but the absolute value diverges. Therefore, let's write that out. Yeah, since n converges, but the absolute value diverges. This is conditionally convergent. I noticed on this one, you've got negative 1/3 plus, it's like negative 1 over 3 squared plus 1 over 3 to the third plus 1 over 3 to the fourth. This is not an alternating series. As the signs, see how the signs change in pairs, right? Like it's a negative, it's a negative, it's positive, right? So this is not alternating. So note though, oops, I wrote that wrong. Let's think about the absolute value of this for a minute. So if I take out the alternating part, which is this numerator up there, then I'm just left with that part, right? Which is the same as 4 1/3 to the n, right? That's the same thing. Which is a geometric series with r being 1/3, so my absolute value of r is less than 1, so it converges. Therefore, we know if the absolute value converges, we can conclude then the original a sub n will also converge. Remember, the converse is not true though, but this is true. If the absolute value converges, the original will also converge. And so, if they both converge, this is absolutely convergent. All right, notice the signs do alternate here. So we're going to apply the alternating series test. So number one is the limit. The part that's not alternating, does that equal 0? The alternating part's that numerator there. So I just got that. So if I run that natural log of infinity on the denominator there, sure, that equals 0. So this is true. Condition number one is met. So then the question becomes, is this true for all n? Is 1 over natural log of n plus 1 less than or equal 1 over natural log of n plus 1? In other words, does 1 over the natural log of n plus 2, is that less than or equal to 1 over natural log of n plus 1? Sure enough, that is true also, right? So by alternating series test, this series does converge. So then the question is, so what about the absolute value? Well, that would just be the non-alternating part. So let's use a direct comparison with just 1 over n. That'll be less than or equal to 1 over the natural log of n plus 1, which is our an. So since the smaller series 1 over n diverges by the p series, one over n to the p, so p is the 1, right? So p is less than or equal to 1, greater than 0. Then, so if this smaller series diverges, then the larger series must also diverge. Alright, so what can we conclude? Therefore, we know that one converges, but the absolute value diverges, so it is conditionally convergent. Conditionally convergent. Notice the terms do alternate, so we'd apply the alternating series test. So number one is the limit and goes to infinity of the non-alternating part. Does that equal 0? So this is the alternating part, right? The negative 1 to the n plus 1. So we're just looking at the 1 over n squared. Well, 1 over infinity does equal 0, so that's true. So a to the n plus 1 less than or equal to a to the n for all n. Well, oops, what am I doing? There's no limit here. That would be 1 over n plus 1 squared. Is that less than or equal to 1 over n squared? Yep, that's also true. So by alternating series test, this series does converge. This does converges. Well, since it converges, now we got to think about the absolute value. So let's examine the absolute value. Well, that's just saying every term's positive, so that would be the 1 over n squared, which by p series with, this is 1 over n to the p, with, so our p here is 2, so being bigger than 1, converges. So we know the absolute value converges. So we can make our conclusion. Therefore, since a to the n converges and the absolute value converges, then our original series here is absolutely convergent. So on this one, the signs do not alternate. They do contain positive and negative terms, but I can't apply the alternating series test because it doesn't go positive, negative, or vice versa, right? But we do know, that's really bad, we know that the sign of n values are always between negative 1 and 1, right? So if we divide everybody by n squared, and so I'm going to use b of n to be this right-hand side. Because I know that's the larger one, it'll converge, right? So the smaller one, sine n over n squared, must converge. And so we will use b sub n 1 over n squared, since by p series p equals 2, it converges. So by direct comparison, we have the a sub n is sine n over n squared. That's less than or equal to the 1 over n squared. That's our b sub n. Since the larger series converges, then sine n over n squared must also converge, also converges. All right, so we know this thing converges. So now let's examine the absolute value. So if this was just all positive values, right? No negative values on this. So sine n over n squared, right? Well, that's the same as the absolute value of the top over the bottom, right? Absolute value of the top over the bottom, and so on, right? Which, again, by direct comparison, the absolute value of sine of n is going to be less than or equal to 1. And so the absolute value of the sine of n over n squared would be less than or equal to 1 over n squared. And we know this larger one converges. So the absolute value one also converges. The smaller one must converge. If the larger one converges, then the smaller one we're comparing it to by direct comparison also converges. Now we make our conclusion. Therefore, since n converges and so the value of an converges, we know sine of n over n squared is absolutely convergent. Well, thanks so much for watching. See you next time.